What's up, guys? So today we're going to be doing another derivative question. This time we're using probably one of the most challenging derivative techniques that you're going to learn in grade 12 calculus, which is implicit differentiation. Now, implicit differentiation is really just an application of the chain rule, which says that if you take the derivative of a function of x, and there's sort of one function within another one. So I'll give an example here. Let's say we have something like x squared minus 2 to the power of 7, the derivative of that is going to be 7x squared minus 2 to the 6 times 2x. And what happened there was we essentially took the derivative of this like outside function, this like power of 7, using the power rule, right? We just brought the 7 out front and subtracted 1 from the exponent. But then the additional step was we needed to multiply by 2x, and that was just the derivative of the inside part of that function. Right, so the chain rule just says that if you have a function inside another function, so kind of like x squared minus 2 inside, something to the power of 7, the derivative is the derivative of that outside function, leaving the inside alone, multiplied by the derivative of the inside function. Okay, now the reason that this relates to the chain rule is the variable that we're always taking the derivative with respect to is going to be x. But how do we take the derivative of y? Well, y is tricky because y is a function of x. But the thing is, we don't actually know what that function of x is, right? If I say y is e to the power of xy like we have in this example, well, we can clearly see that y is a function of x because there's an x included here, but there's another y going on in the exponent, so it's hard to determine that exact relationship. Now, what that means is every time we take the derivative of y, we have to multiply by the derivative of y. Now, what I mean is, let's say we have like a y squared. Well, when we take the derivative of y squared, what we need to be careful about is the derivative is going to be 2y, but y is a function of x, which means we need to be careful to multiply also by the derivative of y with respect to x. Now, there's two ways you can write that. You can also write it as y prime, but basically what that is, it's just a placeholder saying, hey, I'm not really sure what the derivative of y is with respect to x, so I'm just going to like throw in a general term, so like dy over dx or y prime, depending what you prefer, which is just like representative of the derivative of y with respect to x. All right, so let's see if we can apply that with this question here. So what you have to do when you're doing implicit differentiation questions for the most part is take the derivative of both sides. So if I take the derivative of the left side, the derivative of y is just going to be dy by dx, which just stands for the derivative of y on the top with respect to x. All right, and that is going to be equal to the derivative of e to the xy. So how do we do that derivative? Well, remember with e, what you always do is you just leave it and then multiply by the derivative of what's in the exponent. So in this case, that's sort of like a product rule. We have to think about what's the derivative of x times y. So using the product rule, we'd say the derivative of our first term, x, is just 1. And then if we multiply that by y, we just get 1 times y. All right, plus the derivative of our second term is going to be dy by dx. We're just going to multiply that by our first term, which is x. Okay, so I don't actually need to write this little 1 here. It's kind of just taking up space and making things look more complicated, but this is essentially what we have. All right, so this looks like an absolute mess. Now, what we're actually trying to find here is dy by dx. And we need to isolate dy by dx because this isn't really a solution, right? Because we've got another dy by dx over here. So this doesn't give us an exact relationship between dy over dx and a function of x and y. So what we need to do is find a way to get the dy by dx's on one side and then to isolate them. Now, in general, the process that you want to take here is bring the dy by dx's or y primes, whatever you're using, onto one side, and everything that doesn't have a dy over dx or a y prime, leave it on the other side or bring it over if necessary, and then factor out the dy by dx or the y prime. All right, so to do that, if I want to bring this term over to the left side, I'm going to need to distribute in this term first. So to do that, I'm going to end up with dy over dx on my left side is equal to e to the xy times y plus e to the xy times dy by dx times x. All right, so now I'm going to take this term here and bring it over to my left side. That way all of the dy by dx's are on one side. So I'll have dy by dx minus e to the xy dy by dx times x is equal to e to the xy times y. All right, now the last thing that I'm going to do here is I'm going to try to factor out the dy by dx on this side. Because the point of us doing this was now all the terms on the left side have a dy by dx, right? So we can totally factor that out. All right, so if I factor out dy by dx, I'm going to have 1 from this term minus x e to the xy from this term. And I know I rearranged it a little bit. I kind of put the x in front of the e to the xy because it looks a little bit nicer. But you certainly don't have to do that. All right, and I'm going to do the same thing on the other side to make sure this looks as clean as possible. I'll write this as y e to the xy on the right side. All right, so now that that's factored out, what we can do is just divide by the sort of chunk that we factored it out from. So dy by dx totally isolated is going to be y e to the xy divided by that term in brackets. All right, and now that's it. We've got our dy by dx in terms of variables x and y exclusively. Now, if the question had sort of a part B, like find dy by dx or find the derivative of the function at a particular point, or find the slope of the tangent, I should say, let's say at the point 1, 2. I don't think that exists on this function, but let's say hypothetically it did. The only difference between this and sort of regular derivative problems is rather than just plugging in the x value, you're going to plug in both. So you're going to plug in values for y and x, and then sort of simplify until you get a numeric solution. But in our case, we're done with just the derivative, so we'll leave it at that.